Welcome everyone, and it's a pleasure to be here. Again, I'm just across the street, so if you have any question you don't want to ask now, you can always feel free to shoot me an email or just stop by my office. So today I'm going to talk about some recent work with my collaborators on integrative analysis of multiview data with emphasis on dimension reduction and prediction. So I believe no one would argue with me that we are now in the big data era. So tens of millions of gigabytes of data are generated every day around the globe in finance, social media, healthcare, and all kinds of fields. So the huge amount of data allows us to understand ourselves as well as the world around us like never before. So it's a great opportunity for us, for statisticians, bioinformaticians, and all kinds of data scientists to get a handle on this. But at the same time, the large volume, variety, velocity, and veracity of data really creates a huge challenge to data generation, translation, storage, and as well as analysis. So there are a lot of challenges as well in this field. So how to deal with this big data problem is a huge topic. I'm not going to give you some magic solution today, but I just want to focus on one specific aspect of big data, that is multiview data. So what I mean by multiview data is data that are measured on the same set of samples, but from different sources. It has become more and more popular nowadays, especially given the decreasing cost of data acquisition. So now people have the luxury to measure different aspects of the same subjects, trying to get a more comprehensive picture. So that's really the starting point for this multiview data analysis. Let me give you a few examples. Some of you may be familiar with this, the Cancer Genome Atlas project. So it's a huge collaborative effort that try to understand the cancer mechanism. So people have collected genetic data at different molecular levels, such as DNA mutation, copy number variation, methylation, gene expression, all kinds of genetic data at different molecular levels, trying to understand how these data at different levels interact and how they jointly lead to cancer. So ideally, by integrating data from different sources at different levels, we can get a better understanding of the cancer mechanism and in the long run lead to a cure to cancer. So that's one example. All this data are measured on the same tumor samples and adjacent normal tissue samples. So this is definitely fits in the definition that I gave here for multiview data. Another example which I'm more familiar with is the GTEC example, the Genotype Tissue Expression Project, where the ultimate goal is trying to understand the genetic and genomics, the similarity and difference between different human tissues. So people have collected genotype and gene expression data in different tissues from the same set of donors. Again, this is multiview data measured on the same samples but from different sources. Each tissue can be viewed as a source, and the idea is try to integrate the information that we get from different tissues from the same subjects and try to understand the genetic behind it. And also, there are other examples such as the Human Connectome Project, where for the same set of humans, we kind of measure their connectivity in brain, both using all kinds of platforms like EEG or functional MRI, try to get a good understanding of the structural as well as functional connectivity in human brains. So all these are examples, let alone the electronic health records example where we have data for a patient's medical history as well as their all kinds of diagnosis and lab results. So those are all standing examples of multiview data. It's really prevalent, and it has gained a lot of interest in the field. But the key to understand the power of multiview data is to do integrative analysis. So by integrative analysis, I mean we look at all the data together and try to make sense out of it, rather than looking at each piece and do standard analysis and piece together the results. So each modality may provide a partial view, and jointly looking at all modalities may give us the whole picture. But as I mentioned, the integrative analysis needs to be done at the global level. We need to look at all the data and analyze all the data simultaneously in order to get a good result. Piecing together the results from individual analysis does not really give us what we want. After all, it's like the blind man and the elephant. If you piece together a snake, a spear, a fan, a rope, a trunk, it doesn't give you an elephant. So that's a key for harnessing the power of this multi-view data. So we need to do the real integrative analysis. There are a lot of challenges associated with the integrative analysis of multi-view data. So here I just listed a few challenges specifically relevant to statistical analysis. One challenge is different views have shared, partially shared, and specific patterns. If you think about the genetic data from TCGA example, all these data views, they are not independent. These share some underlying commonalities that is the driving course for cancer. But at the same time, they have their specificity. So how to tease out different parts of these patterns is one challenge. And another challenge is that when you integrate multiple views, they may have different data types. They may have different dimensions, different scales. So it's not as simple as just putting them together and concatenating them as a big data matrix. It's much more complicated than that. So again, using the TCGA genomic data as an example, we have categorical mutation data. We also have continuous expression data. And sometimes we even have more complicated like network data from all kinds of sources. So how to integrate data with heterogeneous types is another challenge. And I believe many of you are very familiar with the high dimensionality curves. Previously, when we look at one data view, the high dimensionality gave us a lot of trouble. Now we're looking at multiple views simultaneously. So the high dimensionality the problem is even more severe. So how to handle that huge dimension with limited samples is a stunning challenge. And another challenge is incomplete observation, meaning that we don't have the luxury to observe all the data at all time, especially with multi-view data. So some individuals may have measurements for some of the views, but not all, which gave rise to a new missing mechanism, what we call the blockwise missing. So it's kind of new. So even the experts in missing data analysis doesn't really have a good handle of how to deal with this type of missing data. So there's also some severe challenges there. And there are lots of other challenges that I don't have the space to list. But the bottom line is integrating data from multiple sources is much more complicated than just putting them together and doing what you used to do. So it involves a lot of new thinking and new methodology for dealing with this type of data. So in the statistical literature, there has been some previous work that try to get a handle on this type of analysis. Among them, what I mostly interested in the dimension reduction framework that kind of serve as a good foundation for all the follow-up analysis. One of the seminal work is called the joint and individual variation explained method, or JIVE. So the idea is very simple. Assume that we have multi-view data. One thing that we can do to get a better understanding of the data structure is to stack them together, try to decompose them into the summation of several different structures. One is joint structure that is shared across all different views. One is individual structure that is specific to each view, but orthogonal between each other. And the remaining can be viewed as noise. So the idea is very simple. We stack all the data together and decompose them into different patterns. And then once you achieve this, so I won't talk about the actual detail of how to do this, but assume that we have achieved this. Then you can use the joint structure and individual structure, which reside in the much lower dimensional, dimension space to do further analysis. For example, if you care about using the multi-view data to do classification, you can use the joint structure and see how it's related, how it can be used to do classification or clustering. If you are particularly interested in, for example, the specific structure corresponding to one view but not confounded with other views, you can look at the individual structure from this pattern. Okay? So all in all, this type of idea gives us a very good starting point to tackle this multiview data problem. Similar ideas have been explored in a lot of literature and have shown to be very useful in practical examples. More recently, we have done some work trying to further generalize this idea to deal with partially shared structure, non-Gaussian data, and blockwise missing data. So we have a couple of publications in that area. So if you are interested, you can go to my website and check the literature. But what I'm trying to say here is dimension reduction can serve as a good starting point for dealing with multiview data. But today, I'm going to switch the focus a little bit and talk about a particular question that we're trying to address in the field of multiview data analysis, that is multivariate regression. So our goal here is trying to leverage the multiview data, which are represented by this X1, X2, X3 block. You can have much more views, and jointly using this data to predict a multivariate response Y. Okay, that's a very standard question in statistics, and I'm just going to show why the standard method doesn't work and why we need some new methods to particularly take into account this data structure. So again, our goal here is to do prediction. We want to do multivariate prediction where we have multivariate response Y and multiview predictor that can be represented as different data blocks. They are all measured on the same set of samples, so it clearly satisfy our definition of multiview data. So there are a couple of challenges with this type of setup. One is that clearly there are multiview predictors, so which is not the standard setup that we are used to in multivariate regression. Another challenge is that in many real data problems, we say that the response variables, they can be non-Gaussian. They can take values like binary values or categorical values. So standard least square approach does not really work in that situation. And above that, we may have missing values. So again, standard methods does not really know how to handle missing values in response without hurting your power. So that is the setup of today's talk. And this problem is motivated by a real problem. So this is motivated by a longitudinal study of aging, which is a collaborative effort of National Center for Health Statistics and NIA. So the data is collected for a period of time, and it was originated in 1994 from National Health Interview Survey. And then there are two follow-ups. One is a Wave 2 data from 1997 to 1998, and another is a Wave 3 data, which from 1999 and 2000. So the population that the study focuses on is the senior population with age 70 years and older. And in each survey, in each wave, people have measured their health conditions, living conditions, family situations, medical conditions. All kinds of measurements are taken for this studied population. So the idea is trying to get an understanding of what factor actually affect the elderly's health condition. So they try to use this longitudinal study to get a good understanding of that. In particular, one of the goals of the study is try to provide new information on individual health risks and behaviors in elderly, including alcohol and cigarette use of hormone replacement therapy, receipt of important health screenings such as mammography and prostate exams, body mass and weight loss, physical activities, and diet and nutrition. So that's one of the listed goals in this study. So by thinking about this problem, it can naturally be formulated as a prediction problem. So we have these longitudinal measures. So a natural approach is to use what data we collected from the previous time points to predict the health conditions for the future time point, and then validate using the data that we collected on the new data, right? So it can be naturally formulated as a prediction problem. And moreover, if we look into the data, it actually gives us the motivation why we want to formulate this as a multi-view predictor and a multivariate response prediction model. So in particular, if we focus on this wave 2 and wave 3 data and use wave 2 as predictor and to predict health outcomes in wave 3, then we can see that if we look at the wave 3 data, there are lots of responses that are related to the health outcomes, such as cognitive, sensational, social, and life quality outcomes. These are all can be viewed as health outcomes that we want to predict. Okay? And furthermore, these outcomes, most of the questions, they are binary. They just ask you yes or no. So the answer is binary. And many people have missing entries in the survey, so it naturally gives rise to the missing value. So that is our response variables. It's multivariate, is non-Gaussian, and it may have missing values. Okay? And in terms of the predictors, each wave gave a very rich information about the health and the life condition of this population. It contains rich information about the health risk and behavior measurements. And if we further look into those questions, it can be naturally categorized into several groups, which fit our definition of multi-view data. Okay? So some questions may be related to their health conditions. Some questions may be related to their family relations. Some questions may be related with their previous medication histories. So all these, each group, they are very homogeneous within each group, but between groups, there are a lot of difference. So it naturally can be treated as a multi-view predictor. So that's kind of the starting point of why we want to develop this method. So all in all, if you look at this example, this prediction example, it naturally fits into the framework that I introduced in the previous slides. That is, we have multi-view predictors, and we want to do prediction, where our response is multivariate, non-Gaussian, with missing value. Okay? So this is our motivation. And ultimately, we want to use wave 2 data to predict the health outcomes in wave 3. And that's the starting point. Okay? Any questions so far? So in order to address that question, we developed this new method called integrative reduced rank regression. So next, let me move on to some technical details about how we set up this model and how we estimate the parameters that we are interested in. So there are a little bit of formula. I try to limit the formula in the slides, but let me know if anything is unclear. Okay. All right. So again, our goal here is try to predict a multivariate response Y using the multiview predictors X. So let us start from the simple case where Y just contains continuous responses. All right. Assume we have a response variable Y which is of dimension n by q. We have n subjects, common subjects that are measured across different views and also on the responses, and q response variables. So it's multivariate. And in terms of the predictor, we denote the predictor as X, which is a combination of x1 to xk. We have k views, and each view may be multivariate. Okay? Each view, we denote the dimension to be n by pk. So pk might be much larger than n. So that's the high dimensional problem that I talked about before. But since they are measured on the same set of samples, one simple way to make the notation simple, we can combine them horizontally and put them in X. Okay, so that is our predictor matrix. So the X predictor has dimension p, which is the sum of individual dimensions of each data matrix. So the simplest model that we can use to deal with this prediction problem is just this simple linear regression, right? We just write Y as a linear combination of this multivariate multi-view predictor X times this coefficient B0 plus some noise, E, represented by E. And it has an equivalent form which, if you write it out, is essentially the sum of each individual view multiplies corresponding coefficient matrix plus the noise term. So this is nothing new here. It's just the standard multivariate linear regression model. Okay, the simplest thing that we can do. But there are a couple of challenges, as you can see, associated with this method. One is that here, what we do is we just concatenate all the views without doing anything else, right? But potentially different views may have different dimensions, they may have different scales, they may have different relevance. But if we just concatenate them, essentially we treat them as exchangeable. We don't really differentiate different views. Imagine that some views may contain a lot of variables and may have large scales in terms of the measurement, then it naturally dominates all the other views, regardless of whether that view is really important or not. And similarly, if a view only have a few variables, then even if it's very important in predicting the outcome, it will be naturally downweighted because of the way that we formulate this regression model. So that's one challenge that cannot be addressed using the standard method. Another challenge is, again, high dimensionality. Each view may be high dimensional, and the concatenation of multiple views, the dimension can be even higher. So standard regression method, we cannot get a closed form solution due to the singularity problem. So that's another challenge that cannot be easily addressed using the standard approach. And also, in many cases, it's reasonable to believe there are some underlying driving factors that are more interpretable, which predict the outcome. But this model definitely does not reflect that, that belief. So we need to do additional stuff to capture that underlying driving factors. And finally, again, as I mentioned, this model is just suitable for for continuous responses with no missing values. What if we are dealing with missing values? What if we are dealing with the standard method doesn't work and we need some new approach? By looking into the literature, there has been some methods that developed that partially address some of the challenges I mentioned before. One class of method is called the group sparse method. So the idea is, instead of treating all the variables as exchangeable, we just treat them as different groups of variables, partially taking into account the multi-view structure. But the way they take into the multi-view structure is very naive. They just treat each view as a group of variables. So by imposing some regularizations, you can select all the variables in that group or kick out all the variables simultaneously. That's how they take into account the multi-view feature of this data. So it achieves some sort of multi-view learning idea, but not very sophisticated, and not in a very sophisticated way. Okay, and at the same time, the disadvantage of that class of methods is that essentially it ignores the latent factors for each views, so it doesn't really have very good interpretation. Another class of methods is called the low-rank methods. So it's quite the opposite of the group sparse method. It doesn't treat multi-view data as different groups of data, but just look at them as one group of variables and try to get the underlying driving factors using the low-rank technique. Again, it can identify latent factors, but it ignores the heterogeneity between different views. So it doesn't really achieve what we want to achieve here. So our question is, can we come up with some method that kind of bridge these two types of methods and jointly address all the questions that I raised in the previous slides? It turns out this can be achieved using this integrative reduced rank regression idea, where graphically you can think about the method is doing something like this. So for each view, x1 to xk, essentially we're trying to get some low-rank latent factors from each view with the help of the responses, which is denoted by x1 v1, x2 v2, and x1 u1, x2 u2, and all the way to xk uk. So those are the latent factors that we learn from data, not only the multi-view predictors, but also the responses. And then we can jointly use those latent variables to predict our multivariate response. So it naturally connects both classes of methods, the group sparse method and low-rank methods, in the sense that for each data view, we try to learn a low-rank latent structure, right? But if the latent structure has rank 0, essentially it means the entire group does not contribute to the response. So then in that end, it connects to the group sparse method. On the other end, if we put some regularity conditions on the structure that we impose, the U's and V's, it naturally reduces to a low-rank model. So that way, it actually connects both methods and connects both ideas to address this issue. Okay? So that's the initial idea. And in order to achieve that, we need to do much more work to lay down the mathematical framework. But in the simplest form, this is how we can address, how we can achieve the structure that we imposed in the previous slide. So we can estimate a model parameter using this penalized regression framework. So the top minimization problem is what we are trying to address. And as you can see, the first term is a least square term, which is the same as before, which is the same as the standard multivariate linear regression. But what's new is the second term, the regularization term. So if you look into the regularization term, you can see that it's actually a sum of separate nuclear norm penalties on each individual regression coefficient bk corresponding to each view. It is well known in the statistical literature that the nuclear norm penalty induces low rankness. In other words, as long as we impose the nuclear norm, we can get low rank structures on the coefficient. Yes, question?
What's a nuclear norm?
Nuclear norm for a matrix is the sum of the singular values, the absolute singular values. So that can be viewed as the convex surrogate of the rank constraint. So think about, if you are familiar with lasso penalty is actually a convex surrogate of the L0 penalty, which is restricting how many non-zero parameters you have. So similar here, this nuclear norm can be viewed as a surrogate of the rank constraint. So that's a statistical reason behind why it can induce low rankness. So the idea is that we're trying to impose this nuclear norm penalty for each individual regression coefficient matrix bk corresponding to each predictor xk, each predictor matrix xk. And that way, we can induce low rankness. Okay? But the actual mathematics is much more complicated than this. There are a lot of technical details that I don't want to bore you here. But the idea is that once we have a low rank structure estimated for this BK matrix, it can be naturally represented as a UK times VK transpose. And with simple algebra, you can say that xk times uk now becomes a low dimensional latent factor that can be used to predict y. And the vk is the corresponding new coefficient corresponding to this latent factor. Again, as I said, there are a lot of technical details, such as how to choose the weight that balance different views so that different dimensionality and different scale does not really affect our result, and all kinds of other things like how to choose a tuning parameter. So those are the technical details that I'll omit here. The bottom line is this specific setup, if we set specific regularity conditions based on this framework, it naturally connects to the standard reduced rank regression model, the group lasso model, multitask learning, and many other existing methods. So it's really a very flexible framework that covers a lot of existing methods as special cases. And in terms of computation, at the end of the day, we want to fit that model using data and try to estimate the corresponding coefficients to make inference. So in order to do the computation, in order to solve that optimization, we also do a lot of work in that direction. One thing to notice is that the optimization, the objective function in the previous slides actually is a convex objective function, so which makes the computation not so complicated. So we can address it in a very reasonable time frame. And in particular, we propose to use this alternating direction method of multipliers algorithm to address it, which is an iterative algorithm and has nice convergence property for this convex problem. So far, the framework has been proposed for non-Gaussian data, since we have this first least square term. But it can be easily generalized to non-Gaussian data to handle missing data as long as we introduce this majorized minimization algorithm to deal with the non-causality and missingness. Tuning parameter can be selected using cross-validation, and we also derive some non-asymptotic estimation and prediction bounds for this estimator from this model. So all in all, what I'm trying to see here is that this is a solid method that we have some statistical guarantee about the performance of the approach. There are a lot of technical details behind this, which I'll omit here. So I guess what's more interesting is we want to say how well this proposed method does compared to the existing methods on some numerical examples. So we've done very comprehensive simulation studies trying to validate the proposed approach. And in most examples, the proposed method outperforms existing methods, which the obvious reason is that the proposed method is a general method that can subsume many existing methods as special cases. So no wonder that in different situations, it performs favorably compared to the existing method. At least it's not worse than any existing method. But in some situations, it may gain a lot more compared to the existing methods. For example, here is a quick peek of one of the simulation setting where we have 3 views as our predictor, and the dimension is set to be 500 samples, 50 variables per view in the predictor, and our response have 100 dimensions. In reality, we set the coefficient for the first 2 views to be low rank with rank 10, and the third view to be not important. In other words, the coefficient for the third view is 0, just a 0 matrix. If we apply different methods to this without knowing the actual true generative model, we can say that the 2 variants of our proposed method, the RRR and IRR/A, A stands for adaptive, they significantly outperforms the other competitors in terms of the mean square prediction error. So which means by taking into account this specific multi-view feature of the predictor and the low rankness, we can gain a lot of more power compared to the existing method. Okay, so that's the general message from the simulation study. So here I only show you one peek of the more comprehensive simulation studies. Okay, and next we apply this method to the real data, and we want to say what new insights can we gain from this new method. So recall that our motivation is this longitudinal study of aging. So we want to use, our ultimate goal is to use wave 2 data to predict the health outcomes in wave 3. The data have almost 4,000 common subjects between the 2 waves, and we particularly focus on 41 binary health outcomes from wave 3 that covers cognitive, sensational, social, and all kinds of health outcomes. And among those outcomes, about 20% have missing values. So they're just missing sporadically, so we just assume the missing is missing at random. Okay? And in terms of the predictors, we get useful information from the wave 2 data based on the meaning of each question. We can classify them into 5 different groups. We have 38 housing conditions, about 60 family statuses, 40 daily activities, 114 prior medication conditions, and 40 medical procedures. So these are kind of, so we determine this category. This is just one way to classify the predictors into different views. If it can be further improved if we have more, if we have better way to classify the predictors. But this is just I just want to use this as a proof of concept to show that by separating the variables into different groups and treat them as multi-view, we can gain more understanding of the real data analysis compared to the competitors. So this is just one way of classifying them into different views. So this is the data we have, and our goal is trying to use this x1 to x5 to predict y. Okay? So what we do is we compare the proposed method the IRR with some existing methods. In particular, there are two methods that can be used here in this example. One is the generalized reduced rank regression, which doesn't really respect the multi-view feature of the predictor, just treat them as one giant predictor matrix, but it can handle the non-Gaussian multivariate response variables. So that's one competitor, generalized reduced rank regression. Another competitor is the GLMNet, which is the combination of logistic regression with lasso penalty or elastic net penalty. So it is applied to each response variable at a time, ignoring the grouping feature of the predictor. Okay? So it just applied to each individual response one at a time and using all the variables as predictor. So that's two commonly used predictor, commonly used competitor in the literature. In order to compare, we separate the sample into training and testing. So we use 3,000 as training and 988 as testing, and repeat the procedure 100 times in order to get the confidence intervals. So the criteria that we use to compare different methods is the AUC for each outcome. So recall that each outcome is a binary outcome. So we use the 3,000 samples to train and then predict on the remaining 988 samples in terms of their prediction power. So you can get an ROC for each outcome, and then you can calculate the AUC for each outcome. So that's one criteria. Another criteria is more of it's combine all the prediction performance for different outcomes, for different 41 outcomes, that is the average deviance. At the end of the day, these two criteria give similar results. So here the figure just show you the AUC for each of these 41 outcome across different methods. It may be hard to see, but the message here is that the proposed method is always among the top compared to the alternative methods in terms of the prediction power. So here, these are the outsample AUCs, so which really reflects the true prediction power of each method. And in particular, on the x-axis, it's ordered based on the missing rate. So if you take a closer look, you will see that the proposed method gain more when the missing rate is higher, in the sense that it can leverage effects across different views and borrow strengths across different response variables. So that's why it gains more when the missing rate is more. So that's the general message that we can get from this prediction accuracy. What's more interesting is to look at the coefficient matrix that we estimated using different methods. So here is the heat map of the coefficient matrix that we estimated from different methods. On the left panel is the matrix estimated from our method. Middle panel is the generalized reduced rank regression, and the right panel is the GLMNet. So if you look across different methods, the common message that is shown from this estimate is that, by the way, the different bars here separate the different data views. So here is just the heat map of all the coefficient matrices concatenated together after the estimation. So as you can see, the second block and the third block has brighter colors, which means they are more important in terms of predicting the outcome. So when we check what they are actually family statuses and data activities, which means these two groups of variables are actually more predictive of the health outcomes for later years for the elder population. Because that's one seemingly to be one common message that is all different methods tends to share. But if you look into further more subtle structures, you can say that the proposed method actually does what it's supposed to do, that is to identify latent structures specific to each data view. In other words, if you look at each corresponding block for this IRR coefficient estimate, it has separate low rank structure. So by decomposing it into the lower rank representation, we can get a better understanding of the latent factors that actually drive the predictor. But that's not the case for the other two methods. For GRR, essentially it just identifies one huge latent factor corresponding to all the variables. For GLMNet, since it's a sparse method, it only identifies individual variables that is predictive of the outcome. It doesn't really give you the latent factors. So in terms of the prediction, in terms of the interpretation, we deem the proposed method to be more interpretable and have better utility in translating this research into real practice. But one thing that I do want to acknowledge is that if you compare the AUC or the average deviance between different methods, it turns out the IRR method and GRMNet does not really have huge difference. We only get a slight advantage over the GRMNet, which means although we tackle the problem from different perspectives, one is more from low rankness, one is from a sparsity, they share some merit in terms of prediction. So in the long run, maybe a future research direction is to combine strengths of both methods and try to come up with something that's even more powerful in terms of prediction performance. So just to briefly summarize what I covered today, so we propose this integrative reduced rank regression method, which try to address the multivariate regression problem with multi-view predictors. With the specific setup that we propose, it bridges the low-rank models and the group sparse models. So it is a very flexible framework that covers a range of existing methods. I hope the method showcases the utility and potential of multiview data. In practice, there are a lot of more things that needs to be done to analyze the multiview data and to harness the power contained in these different views. More recently, we've been thinking about how to use this multiview data for clustering, for classification, and particularly how they interact with each other between different views. So there are, again, as I said, there's a lot of things to be done in this area. And there are a lot of open questions that needs expertise, not only from biostatistics, but also from biomedical informatics and many other fields. We need to join force to tackle the problem brought by big data. So the paper has been published in Biometrics, and feel free to check out if you want to know more details about the technicalities. I'll just stop here. Thank you very much.
Any questions?
Yes.
Could you say a little about how you plan to incorporate relationships between views?
Yes, that's a very good question. So the general idea is for each view there has been a lot of work in terms of the graphical model analysis. So recently we've been thinking about how to generalize that idea to the ultimate goal is trying to get a huge graph that integrate the information between different views, and within each branch you have separate graphs that capture the relation between different variables. So we're trying to tackle this problem from a graphical model perspective. That's kind of the most high-level introduction of what I've been thinking. Yeah, but there are a lot of other methods, I believe.
Are you going into doing this blind, or are you like incorporating prior knowledge? For instance, a transcription factor causes the transcription of the gene.
That's a very good question. We do want to incorporate that additional information, especially at the higher level. When you try to construct the graph between different views, we definitely know a lot of information about, for example, in genomic studies, we know which factor regulates the other factors more dominantly than the other way around. So those information definitely can and should be built into these giant graphical models. That is a very good point, yes.
In the simulation where you specified the rank
Mm-hmm.
of the matrices B, do you find that you can recover the rank once it was clear that the predictive error was lower, but do you find that you can also recover the rank?
Good question. So one thing that people know in common about this nuclear norm penalty is it tends to over-select the rank. So that's something that cannot be easily addressed. It's like lasso, it tends to underestimate the sparsity. So the same thing here, we cannot accurately recover the true rank, but that's why we have different variants of the proposed method that I didn't have a chance to talk about. So this adaptive idea is trying to impose higher weight on the initial estimate, so that for a matrix that tends to be low rank, we're going to put more weight on the penalty so that it can be further penalized. As a result, it tends to have closer estimate of the true rank, and in terms of prediction, as you can see, it definitely gives you better prediction power. But that's a very good point. So I guess in the long run, a possible solution is, instead of using this nuclear norm penalty, we can always think about how to use a non-convex rank constraint, which is computationally is much more complicated. But recently there has been some interesting work. People try to use the non-convex L0 penalty instead of L1 penalty to do a lot of things. I guess we can borrow ideas there to further improve the performance of this method. But that's a good question.
Any other questions? All right. Let's give Dr. Lee another round.
Thank you.